When we begin learning electrostatics, we often use the field point source point formalism. The idea is from an origin of coordinates, there are several position vectors. There's R, capital R, from origin to the field point, that's the observation point. There's R prime, which is the position vector to a source point, in this case, a charge element of a charge distribution. Little r is the relative position vector going from source point to field point. Often we'll do some calculations after learning Coulomb's law. We'll use a Coulomb type field, k dq over r squared, and integrate over a distribution where k is the Coulomb constant, 8.99 times 10 to the 9. Of course, if we have a point charge q, then we simply get the Coulomb's formula kq over r squared. But another result we discuss while discussing charge and charge densities is the fact that as long as you have a spherical charge distribution that has spherical symmetry, then you can still use the Coulomb field formula kq over r squared, provided that you only use the charge within your radius, the charge closer to the origin than you. And that's a result I'd like to try to prove. So, for an arbitrary charge distribution that has spherical symmetry, it would be sufficient for us to consider a spherical shell only, because we could imagine a distribution that has spherical symmetry being a union of many such spherical shells. So we have a hollow spherical shell with a surface density sigma constant, and our job is to have an observation point either outside or inside, and show that when outside, it's as if all this charge is at the center, so we end up with kq over r squared. But when the observation point is inside, we should get the electric field 0. So I have a sphere of radius a, and without loss in generality, if my observation point is along the z-axis, which I'll have horizontal going to the right, that puts the xy plane perpendicular to the screen and going through the center. And then we have theta, 60 degrees, from the z-axis over to this line from center to source point. I'm also showing a ring because we'll see that for source charges along this ring, only the z component of electric field will survive. The x and y components cancel by symmetry. So here's just a few examples. Here's 30 degrees. Here's 150 degrees. So again, theta is this angle here, and I could have z inside or z outside. And so here is an example of one of those hollow spheres, and I'm just showing some notation. Again, if we have r prime is the source point position vector, r is the field point position vector, little r the relative position vector from source point to field point, then what we have is r prime is basically the radius a in that direction, r prime hat. The r vector is basically z in the z direction, z hat. I know lots of books will use k hat for the unit vector along the z-axis, but since k is the Coulomb constant, I'll just use z hat. And then the relative position vector is r minus r prime, and we can show that the z component of relative position vector r is z minus a cos theta. So in any case, the magnitude of little r can be found from the law of cosines, where r squared is a squared plus z squared minus 2az cos theta. And our charge element, 2 pi times the radius of the ring is a sine theta, so 2 pi a sine theta, and then times a d theta to make our ring be sort of a strip of area. Total charge Q is surface area of the sphere, 4 pi a squared times the density sigma. So the contribution to electric field I need to worry about is that z component. So d e sub z is basically k dq over r squared. Now we already talked about the dot product of the relative position little r vector dot z hat, which is z minus a cos theta, and I have the k dq over r cubed. So putting in my charge element and putting in the fact that r is the square root of a squared plus z squared minus 2az cos theta, and since that was cubed, I have that to the 3/2 in the denominator. So I'm going to let b be a parameter that's the ratio of z over a. So you'll see that if b is less than 1, I am inside the hollow shell, and if b is greater than 1, I am outside the hollow shell. If you do the algebra here, you end up with this step here, and a little more algebra. I'm just going to, knowing that the result is that we're going to get kq over r squared, where r is z, we're expecting to get kq over z squared, where q is 0 if we're inside the hollow shell, and it's the total charge q and we're outside. So by writing it this way, I'm getting the result I'm looking for multiplied by an integral. It remains to show that this integral is 0 when b is less than 1. As we said, that means we're inside the shell. And that integral is 1 when b is greater than 1. Again, that meant that we were outside the shell. Now, just to rewrite that integral here, it looks like a mess, but it's actually pretty straightforward. We can just let u equal 1 plus b squared minus 2b cos theta. That also lets me solve for cos theta and du in terms of d theta. This table shows how the limits of integration, where theta went from 0 to pi, in every possible ring where theta goes from 0 to pi, we get these limits on u. There's a little more algebra done here, and in particular, when b is less than 1 as opposed to greater than 1, we would write the 1 plus b squared minus 2b as either 1 minus b squared, because b is less than 1, or in the outside case, b minus 1 squared when b is greater than 1. With that substitution of u, we get this result, and that splits up into these two terms. And this is very straightforward integrals to do with the power rule. For example, u to the minus 3/2 with the power rule integrates as u to the minus 1/2 over negative 1/2, or negative 2, 1 over radical u. And so with those integrals done, we sure enough get that when b is less than 1, we get the 0 we were looking for. When b is greater than 1, we get that 1 that we were looking for. What's interesting is at first I didn't know if the integral would be so straightforward. So I also did this numerically. I have an old video somewhere here, Monte Carlo integration with Excel. And the idea is that with an Excel sheet, I can integrate this function I have here based on using random numbers. A was the radius of the hollow shell. Z was the distance from the center of symmetry to the field point. And essentially the idea is, I'm not going to repeat what's already in my video, and we did solve it exactly anyway. But what I have is, with this method, is that you generate a rectangle of random points, and the integral is basically the area under the curve. So Let me just show that again. So you'll see that as I keep refreshing this Excel sheet, the random pattern generates again, and points are counted or not counted based on them being under the curve as needed or not, and then they're discarded. Turns out for this Excel sheet, I used 18,001 points, and the area of the rectangle is based on the maximum and minimum of the graph of the function. And so we can come up with an area per point, multiply the point count times the area per point, and that gives us the integral. Now you'll see here I have 0.9947. Again, this would be a 1 since z is greater than the radius of the sphere. 1.8 is greater than 0.9. Right, and I can put any values I want here. I could say 2.5 and 0.5, for example. As I keep generating over and over, you'll see 0.9914, 0.9948, 1.139. Right, and you know, if I can keep doing this maybe 10 to 20 times and take an average, and I'm getting the 1. Right, now if I make z 0.8 and a 1.2, for example, then this is what the function is doing here. Then you can see that, you know, area under the curve actually counts as negative when it's above the curve, right? So sure enough, I'm getting numerically 0.0053. If I keep refreshing, negative 0.0048. I keep getting numbers near 0, and if I did a bunch of these, like 10 or 20, and took an average, it would be even closer to 0. So I did it this way as well because I had that video. I thought, what the heck, try and get another view. But it turned out to be simple to do this directly, right? So if I go back, our result that is that for spherically symmetrical charge distributions, we can use the Coulomb field, kq over r squared, if we only use q as the charge within our radius, the charge closer to the origin than us. All right, so let's do some examples. So here are 3 thin concentric spherical shells. So I have 1 coulomb at the 10 centimeter mark, 2 coulombs at the 20 centimeter mark, 3 coulombs at the 30 centimeter radius. So there's several things that you'll want to do. One is you'll want to be able to calculate densities. So for surfaces, that's sigma, surface densities, right? So at a radius of 10 centimeters, for a given net charge, I calculated the density in coulombs per square meter, right? So, for example, this one here, I would have 2 coulombs over 4 pi 0.2 meters squared. And if you do the math, you should get 3.98 coulombs per square meter. Right, so you want to see that you can calculate these densities. Now, for this table here, I'm looking at field points that put us in different regions. At 5 centimeters, we're less than 10. There's no net charge within our radius. There's nothing at the origin, right? The 1 coulomb is the first radius where there is a charge. So with no charge within our radius, we have no electric field. At the 15 centimeter radius, right? So we're in the region between 10 and 20. So the 1 coulomb is within our radius, the 2 and 3 coulombs are not. So Q inside is a coulomb, right? So the calculation I expect to do then is K, 8.99 times 10 to the 9, Q, which is 1 coulomb, over r squared. Now that's our radius, the field point at 0.15 centimeters, 0.15 squared, right? So if you do that calculation, you should get 4 times 10 to the 11th newtons per coulomb. At 25 centimeters, now the 1 and the 2 coulombs are within our radius. So we have a charge inside our radius that's 3 coulombs, the 1 plus the 2. Right? At 35 centimeters, we have all of the charge, the 1, 2, and 3, or 6 coulombs. Right? So in each of these cases, just do kq over r squared, where the q is the q inside our radius, and verify that you get those results. Here's another example. Here's a point at the center, 4 nanocoulombs. We'll also try some metric prefixes in our calculations. So 4 nanocoulombs at the origin, 8 nanocoulombs evenly spread out in a thick, non-conducting shell, inner radius 20 centimeters, outer radius 30 centimeters. So in terms of densities here, we don't have a sigma, we don't have sigmas, there's no surface densities. We have rho, volume density, right? So if we had 8 nanocoulombs on the thick conducting shell, then rho for the thick shell that goes from 20 to 30 centimeters would be the charge over the volume of that thick shell. Now, the volume of the thick shell is related to the volume of a sphere, 4/3 pi, but it would be r cubed for the outer radius, and then subtract off the inner radius. So 0.2 cubed there. Right, so try this calculation. If we leave nano alone, we will end up with nanocoulombs per cubic meter. So give that calculation a try, you should get 100.5. Up to this table here, where we're calculating electric field at different field points, I did the region at 10 centimeters. That's the region between 0 and 20, the air between 0 and 20. Then we did 25, that puts us halfway in the volume of the thick shell. And then I did 35, that puts us in the air where r is greater than 30. Right, so in the regions that are air, right, let's say at 10 centimeters, the only charge within my radius of 10 centimeters is the 4 nanocoulombs. And at the 35 centimeters, all of the charge, 8 plus 4, or 12 nanocoulombs. But in the region halfway in this thick shell, what would be inside our radius is the 4 nanocoulombs at the origin plus an amount of charge equal to the density that we calculated times a volume, 4/3 pi, but now it's not the entire volume from 20 to 30 centimeters, it's only the volume from 20 to 25. So I would have 0.25 cubed minus 0.2 cubed. Right, so when you calculate this amount plus the 4, verify that you get the 7.12 nanocoulombs. Then again, our electric fields are simply the Coulomb field kq inside over r squared. Right, the r for the field point is either 10, 25, or 35. The q inside we calculated, so verify that you can calculate these values, and the units I'm using are kilonewtons per coulomb. Now we have the same shapes, but now the thick shell is conducting. The difference is that the electric field in the volume of a conductor in electrostatics must be zero. Because if it was non-zero, then charges would move. A conductor allows charges to move. But if charges are moving, we have current, then it's not electrostatics. So the idea is in electrostatics, in the volume of the conductor, electric field is zero. So at the 25 centimeter mark, we know we have no electric field value, zero. But since we found that spherically symmetrical charge follows that Coulomb field formula, that also means that Q inside is zero. That means the net charge within our radius must be zero. So if the 8 nanocoulombs cannot be in the volume, the only place it can go is to the surfaces. And the way we can calculate how the 8 nanocoulombs polarizes to the surfaces is to use this idea of Q inside is zero when we're at the 25 centimeter field point radius, right? Because we have 4 nanocoulombs at the origin. Then we must have to negate that at the 20 centimeter mark so that that's a net of zero when we're at 25 centimeters. So minus 4 nanocoulombs ends up on the inner surface of that thick shell. And then by conservation of charge, since this conductor is isolated, 8 nanocoulombs has to be minus 4 plus how much? Well, that's 12, right? So the densities we calculate here are sigmas, surface densities, right? We can calculate the net charge at each radius, starting with the idea that the electric field is zero in the conductor, therefore Q inside is zero, and then working our way from the inside out. So you can then calculate these densities. For example, at the 30 centimeter mark, you should be able to get sigma at the 30 centimeter mark is the 12 nanocoulombs over the surface area of 4 pi r squared. Now I put the 30 centimeters in meters, so we'll leave nano. You should get 10.61 nanocoulombs per square meter. And you should also be able to calculate this one. Right, so the conducting problems, you start with zero electric field in the conductor, and then working from the center outward, figure out how charges end up on surfaces, such that Q inside is zero when you're in a radius that puts you in the volume of a conductor. From there, then, you can use the KQ over R squared, counting only Q inside, right? So very similar to before, except when you're in the volume of the conductor, we have no electric field, no Q inside. That helps us figure out these charge densities. So here's another example, and now our scale will be meters, and I'll use microcoulombs, right? So 8 microcoulombs at the origin, minus 5 microcoulombs, thick shell between 3 and 4 meters, 10 microcoulombs, another thick shell between 5 and 6 meters. So again, there's no volume densities, but we do get surface densities because this is conducting. We can look at various points in different regions, right? So I picked between 0 and 3 meters, I picked 2 meters. 3.5 meters, a radius that puts you in the volume of that inner shell. Then 4.5 puts you in the space between the two thick shells. 5.5, you are now in the volume of the 10 microcoulomb shell. And then 8, you're outside of everything. Right? So again, for conductors, you go to the radii that puts you in the volume of the conductor. No electric field, therefore no Q inside that radius. So starting from the inside out, right, if we have 8 microcoulombs at the origin, we have to negate that at the first inner surface, -8, at 3 meters. At 4 meters, at the outer surface, we have to have the net up to that point. 8 minus 5 is 3. The next inner surface, we negate that 3 with -3. The final outer surface, the net up to that point, 8 minus 5 plus 10 is 13. Right? So at that point, we can calculate surface densities with charges over 4 pi r squared surface areas. Right? So you should be able to calculate these values. While the charges are in microcoulombs, I have densities in nanocoulombs per square meter. Now, up to this table for electric field calculation, at these various radii that put us in these different regions, right, the 3 regions we need to calculate is the 2 meter, the 4.5, and the 8. And at the 2 meter mark, the only charge within our radius is the 8 microcoulombs at the origin. At the 4.5 meter mark, we have a radius that encompasses the 8 and the -5, so that's 3. And of course, when we're at 8 meters, everything is inside, so 13. Again, KQ over R squared, where Q is the charge inside our radius, and you can calculate these electric field values.